Yes, sir, we are making.
It's okay. So welcome back. Today we put at work the Christoffel-Darboux kernel, and I'll show you how moment indeterminateness on the line is controlled by it. So let's review a little where we are. Today's lecture is more theoretical. Previously we saw numerical aspects and all kinds of approximation. Now, when we go to infinity, it's more of a theoretical nature, but I think this is the most important, the central problem in the study of moments. So, mu positive Borel measure today we focus only on the line or maybe a semi-axis. And we assume that is rapidly decreasing at infinity. That means all moments are finite. In short, I'll call such a measure admissible. And if you remember, we defined Christoffel function.
That's x to the n, and what's the exponent is
7.
N. So all monomials are integrable.
right. Yeah, we could read the 7%.
2n.
It was 2n.
Oh, 2.
I was wondering.
To be positive, all moments are integrable. What is the problem?
No, that Cauchy-Schwarz gives you the odd.
Yes, all moments are finite. Rapidly decreasing. I'll call this in short admissible. And we define for any point lambda in the complex plane the Christoffel function as the infimum of the 2 norm square of a polynomial, which is normalized to be 1 at lambda. That was the definition. And also, this is, of course, the infimum of the 2 norm square over p of lambda, non-zero, of course, square, over all polynomials. And if you also remember, this was the inverse of the reproducing kernel. Which in the limit, we discuss it for finitely many steps, but if we go to the limit, this will be simply the sum of the orthogonal polynomials square from 0 to infinity. Pn are the orthogonal polynomials associated to P. This is what we did last time. And we saw what wonders are included in this object. The only question I am addressing today is whether the moments, that means the quantities Sn, determine mu. And it happens that it is not always the case. Contrary to, let's say, other transform. I see this as a discrete transform, as a discretization of the measure in terms of a sequence of numbers. And what means determination? If I take another measure, sigma equivalent, by definition this means the same moments. The main question is sigma equal to mu.
Oh, that's a good question. Is the mass finite? of the measure.
Here?
No, of the measure. Mu. Is it?
Of course, if the square is integrable, the mass is also integrable. You can put 0 here, no discussion. If the square is integrable, it's under, no problem. So, that's the main problem. We have, of course, in mathematics, other transforms. The most important is the Cauchy transform. If we are on the semi-axis, we can speak about the Laplace transform. And the advantage in this thing, so this is a discrete transform, this is a continuous one. Here we have complex analyticity. Here we have also complex analyticity. So these are analytic functions, and as you know, they determine, there are inversion formulas, they determine the measure. So there is no loss in these transforms, while here we have a loss. And we'll see what is the trade between these two. The main result I want to talk first, and I'll give you almost a full proof, is a theorem due to Hamburger. Not Hamburger. He was a follower of Stieltjes. Today, Stieltjes will be our main hero. It's there in the photo. But it's very instructive because it goes straight into the construction of the measure and the way we want to tackle this question. So again, the Christoffel function is the main character here.
Indeterminate efforts, not determinate. I thought if this lambda mu would be positive, then mu would be determinate. But you're saying it's the other way around.
We'll see. Just a second. Okay, so let's try to do the proof. If lambda is 0, then it is determinate. It's if and only. Assume that for such a lambda, this is 0. So what it means, we look at the denominator there. It means that the series in the denominator diverges. Okay? Now, what it is remarkable, and I want to stress this, the Christoffel function depends only on the orthogonal polynomials, and they are the same for all equivalent measures. So if I take all equivalent measures, the orthogonal polynomials are the same. They are distinguished by some other functions, not polynomials. And we do the following. We look at the Cauchy transform. And rather than this, I'll multiply this by P nx. And I write it as follows. Is the usual trick. I add and subtract the value at lambda. Yeah, you follow me. So, what is this? This is the Fourier coefficient in the orthonormal basis of the function 1 over x minus lambda. This is a polynomial in x and lambda. This is coming out, and this is the Cauchy transform of the measure. If I do the same for a different equivalent measure, and so on, I'll have here the Fourier coefficients in the two L2 spaces, Lebesgue spaces. When I subtract, this cancels because it's a polynomial. And this is the same factor, P and lambda. So if I put all this together, I get that the sum of P and lambda square, n from 0 to infinity, times the difference of these Cauchy transforms. Let me write it this way. Is finite, because by Bessel inequality, this has to be finite. But wait a minute. This diverges. Therefore, they are equal. It's not sufficient to be equal at one point. It's an analytic function, we just noticed there. And we need equality of the entire Taylor series to infer that the two Cauchy transforms are equal everywhere outside the real line. Then I do the same for the derivative of this. I take one derivative. And here will be the derivative. What is the deal? This is no more a polynomial, but is a rational function with one pole at lambda. And I know already that they coincide there. So when I take the difference, this disappears. This is summable, is the Bessel inequality. So I infer from here that the derivative is equal. And I continue, and I'll have all derivatives equal at the lambda point. It's an analytic function, therefore they are equal. Therefore, the measures coincide. So, one direction, the easy one, was done. Now, the interesting part is the other direction. Here, I'm trying to do the following. I want to construct as much as possible by hand a different measure which has the same moments, starting from here. And here I'm following the idea of Marcel Riesz, not the original work of Hamburger. And for this we need first a simple lemma, which relaxes a little the definition of the Christoffel function. Namely, I do now the following. I take the infimum of the one norm of a polynomial which is non-negative on the whole line. Yeah, so I take the integral of h, non-negative on the whole line, evaluated at lambda. Obviously, the square of a polynomial is such an h. So I compete with more functions here, so this is less than lambda mu at lambda. You agree? On the other hand, I claim that this is bigger than 1/2 at the point lambda. Here is a fact which I'll review and give you an account in my last lecture. If h is a polynomial which is non-negative on the whole line, h can be written as a sum of two squares of polynomials. Folklore. Already Lagrange knew it, and I think it's very classical.
Nice you mentioned Lagrange.
It's a high school problem to locate. We'll discuss in my last lecture. So let's assume that this is true. Then I want to compete among these quantities. So let's write specifically what we have to do. We take the one norm, here we have to be a little careful because this is complex, so I have to take the modulus. Or rather the modulus here. And among these quantities, so I have two values here. One is bigger than the other, and I claim that this is bigger than, let's suppose that one is bigger than the other, is bigger than q of x squared. And here I can put 2 q of lambda squared. So I make a choice, which is bigger. But this is one of the quantities which enters here. So it's bigger than 1/2 lambda mu at lambda. Very simple observation. So let's put this at work. I have the polynomials. And what is a measure? Now I go a little into the structure, into the fabric of what a measure is. We consider the continuous functions of polynomial growth on R. Polynomial growth. Oh, you don't see. Let me write here.
Sorry, before you erase this,
Yes.
I'm a bit confused about that logic. So here you assume that capital lambda mu of lambda is 0, and then you use
The difference.
yes, and then you use that to conclude that mu is indeed indeterminate.
No, determinate.
Yeah.
Mu is I, sigma then mu is equals.
If it is 0,
Is the probability.
is determined.
It is so you're
Yeah.
calling mu equal to sigma determinate.
Yes, yeah.
Okay, I thought that.
We can put determined here and we can put 0
Yeah.
there. It's the same thing.
No, I understand that. I thought mu equal to sigma means mu is indeterminate.
No, no, no. Follow the proof. So let me erase here. So here is the brilliant idea of Marcel Riesz. We have the polynomials. And here I have the continuous functions of polynomial growth on the line. The integral is nothing else, or over C, as you like. We can work with complex valued functions. The integral is nothing else than a linear functional. Originally, if I have the moments, I know the integral only here. And the question is, how do I extend it? And if you go into the definition of the integral, into the structure, step by step. So let phi be a function which is of polynomial growth, and not a polynomial. Suppose now I erase this, that I have my linear functional only here. I play this game. What value I should assign to the potential integral to phi? Well, has to be bigger than all polynomials which are under phi, and less than all polynomials which are bigger than phi. F and G are polynomials.
Mu is a positive.
Why do they exist? Because of polynomial growth. If I have a polynomial growth function, there exists a polynomial bigger than it and also smaller than it. So these sets are not empty. And these quantities depend only on the value of the integral of the functional on polynomial. So this is known. And now the observation, and this was his major piece of work in the third article on moment problems. Choose any value here and define the extension let's work over R first. As choose any value you want. Now check that this is non-negative. It follows exactly from here. If you know functional analysis, you will say, wait a minute, this is Hahn-Banach. Well, this was before Hahn-Banach.
Yeah. Oh,
This was before Hahn-Banach, and then continue, choose another function, and so on. And by induction, you have a maximal element, which gives you the integral everything. So it's a very beautiful observation, and unfortunately is not that known. So you need a vector space with an ordering rather than a semi-norm. And then you need on the subspace elements to dominate the whole space. This is what we are doing in the order. And then you extend. Now, suppose that we understand this. What if the sup of L of f is strictly less than inf of L of g? F less than phi, g bigger than phi. What if we have a gap? I can choose different values and continue. Therefore, in the end, I'll have two distinct linear functionals which coincide on the polynomials. So if for at least one non-polynomial function this is distinct, there are two measures, let's say mu, equivalent to sigma, but distinct. Okay? We are almost there. So it's the construction of the integral using a Hahn-Banach extension argument. With the lemma we just proved, yes?
Sorry, I was just wondering whether, could you repeat the last one?
So I choose this value differently. The only constraint is that it has to be between these bounds. Choose different
They're
values.
different, you choose two different. But then you get-
And then extend.
I think he is asking how you got the measure.
Yeah.
Finally.
By extending the functional. If I assume that no negative measure on continuous function is
From the functional you recover
Yeah.
the measure.
so this is the brother F. Riesz theorem. Yeah? Okay, so I'll call this a barrier. Such a phi, let's call it a barrier. Claim now I'm using the assumption that at the point lambda this quantity is strictly positive. I claim that this is a barrier. Why it is so? Let's look at polynomials which are normalized in our variational principle, are normalized to have exactly the value 1 at lambda. It means that h of x minus 1 vanishes at lambda. Now, this is a real polynomial. It vanishes at the conjugate point. So it's x minus lambda squared times another polynomial, let's say k.
Rx.
Agree? And what do I know? I know that for polynomials which have the value 1 at lambda, if I take the infimum of the integral, I can put plus or minus here, doesn't matter, so let's put a minus. All k. This is bigger strictly than a constant, let's say gamma bigger than 0. Of course, I have to assume here, using the lemma, that this quantity is non-negative on the full line. Yeah, so according to my lemma, and the bound there with 1/2 Christoffel function, if I run over all polynomials which make this quantity bigger than 0 on the line, they have to be bigger than gamma. So I have a uniform bound from below. Claim the same is happening so this is non-negative. With this, which will be a barrier in the sense of L1, then of course will be a barrier in the sense of L2 also. Why from here to here it is true? I'll say in words. Assume there exists a sequence so that this converges to 0. We have L1 functions. Doesn't mean that this converges almost everywhere to 0, but a subsequence which converges to 0. Choose that subsequence which converges to 0. Then multiplying with this function will obviously converge almost everywhere to 0. This is a continuous function. So along that subsequence, this converges almost everywhere to 0. Therefore, this converges almost everywhere to 0. But by Lebesgue-dominated convergence theorem, this will be 0. Cannot be. So, in short, I cut a little here, it's technicality. Therefore, with our lemma, it simply means, or rather with, I'll rewrite here specifically. It means that if I compete with all polynomials f under or above, I have a gap. This is a barrier. It's exactly what we proved here. Therefore, I can extend and have two solutions. So that's the full proof. Now, Hamburger didn't prove it this way. And the unfortunate part here is that we use Zorn's lemma, we use something which is a little non-constructive. So let's go back to the founders, in particular to Stieltjes. And for the rest of my talk, we'll take a break a little later. I'll show you how Stieltjes and others, Hamburger and Marcel Riesz, reach the same conclusion and much more, analyzed in detail the indeterminateness in terms of orthogonal polynomials in a much more constructive way. So now I turn to the masters.
What's the reference for this? What is the reference for
it is in my slides. And the main tool is continued fractions. Maybe you know them from number theory. It's unfortunate that in function theory we don't teach, we don't somehow touch this subject. It's very beautiful and very rich. And I'll give you a quick introduction based on probably what you know from number theory, and then we'll move into more analytical issues. First, there were numbers. So we start with Euclidean division. And obviously, this will give us the greatest common divisor. And we can write this as a successive fraction. And in the end, we obtain, very handy, the continuous fraction expansion of a rational number. Any rational number, let's say positive, can be written this way. And what is important is this finishes. What happens if it doesn't? It's attributed to Pythagoras' school, but in fact is this Hippasus, apparently, who very ingeniously showed that the diagonal of the square is not commensurable when compared to the side, and found exactly this infinite continued fraction. Therefore, it's not rational. And more general, as you know, you have the square roots of integers, which are not perfect squares. You can write them again into an infinite continued fraction, and this shows that they are irrational, but there is a periodicity here, which is quite interesting. What is so special about continued fractions of numbers? We can represent with this algorithm, taking the integral part of the division successively, any real number. The representation doesn't have ambiguity like the decimal representation or any other representation in a basis. And what it is very surprising is that if we put a topology on the continued fraction expansion of a real number, not only that it is bijective, but from the topology we know from the distance geometry of the real number to the pointwise convergence of the entries in the continued fraction, we have a homeomorphism. So if you are haunted by the construction of real numbers, as I am every year when I teach calculus, I think this is the royal way to do it. Not with Dedekind cuts and not with very painful Cauchy sequences and so on. So everything is displayed, and we have a continuum, obviously, a much bigger set, discretized by a sequence of integers.
This is how Ramanujan thought.
Yeah. It's magic. It's absolutely magic. There is an algebra here which was understood very easily. If you go a little into more complicated than the division algorithm relations, the point is that you have these three-term recurrences. You can divide, for instance, by x1, and you have x naught over x1 is b0 plus a1 divided by x1 divided by x2. So these particular fractions are interlaced by two operations, translation and inversion. And you continue, and there is a simple algebra which was understood very early. When you stop this at a certain point, you get the so-called approximants. And the formal continued fraction will be exactly determined, by P over Q, depending how you start with the initial conditions in the recurrence relation. So it's a finite difference scheme. You start either with 1, 0 or 0, 1, and the approximants of the continued fraction will be P over Q. They satisfy a lot of algebra, very simple exercise, probably you saw it. And you have this beautiful representation of the continued fraction stopped at a certain point in terms of the last quotient. Now, what it is interesting here and important for us, suppose that the entries in the recurrence relation are positive. Then you can estimate immediately the difference between two consecutive approximants, and you see that they alternate sign, positive or negative, depending on n. Therefore, as you know very well, the even and odd have a different monotonicity behavior. Therefore, always they converge. Possibly not to the same number, depending where you start, but anyway, they converge. And that's a phenomenon which is persistent in function theory. I'm speaking here about real entries, not integer entries. Now, the analytic theory goes hand in hand. It's almost the same feature here. And let's start with a very simple observation. Andrei Markov was a big master of continued fraction, like Chebyshev, like Stieltjes. In the 19th century, this was a major topics. And suppose you want to solve this equation. Divide and continue. Z is equal to, and so on. The solution should be this one. And you see immediately that it's converging with what we say. But wait a minute, this converges only to one root of the equation. Where is the other root? If you look at the other root, you will not have convergence. So it's sometimes the behavior depends on how you stop the continuous fraction and how you put the reminder, and this determines the convergence. Now, for entries in the complex field, there are some very simple and useful observations. I put only two of them here. The notation you notice by now is, in short, this one. I borrowed this from Sergei Khrushchev. And exactly as for numbers, if the series is absolutely summable of the entries, the even and odd convergence have limits, but never they coincide, because P over Q obviously is not equal to P prime over Q prime, according to this identity. So, notice that if we have some ability here, we have divergence. Similarly, if we take all entries positive and we take the continuous fraction with 1 over bn as the principal recurrence relation, then converges if and only if we have divergence of the entries. These are easy exercises. You can, if you teach first year, I don't know, real analysis, you can do them easily. It's nothing complicated here. Now, how do we pass from continued fractions of numbers to continued fractions of functions, of elements which depend on a parameter? This was very classical, and one of the roots, not the only one probably, is pi, how we compute pi. And there are endless formulas for pi. There is this infinite product, as you know. And there is a derived continued fraction. So I'll show you how we reach the continued fraction from Wallis formula. So this is really old, and the time of Euler, and very classical. So we start a la Euler with a recurrence relation with an unknown function, which satisfies this identity for S positive. It will turn out that this function is analytic, has some analyticity built in. If we compute the first steps, we see that this is a good approximant of the Wallis formula. And if we have a bound on B for large values, we'll have indeed 2 over pi as a limit. This it is so. And now I'll skip the part, but this is relevant for us. If we assume that this function has a convergent series, let's say towards infinity, of this form, we plug this into the product recurrence and simplify a little, and we'll find a continued fraction. We'll find a recurrence among the coefficients. Very simple. And if we do this, the continued fraction will be precisely this one, which will give us a function now. This is convergent for S bigger than 1, which in the end, when S is 1, will be exactly 2 over pi. Ramanujan found the closed form. This is quite remarkable. And this is in the time of Euler was done. And he could write this in closed form. So I wanted to give you this example just to show that there is a very natural link between continued fraction of real numbers and functions. So,
that one, does it simplify to a polynomial or not? No, sorry, of course.
Yeah, this is a closed form.
Yeah.
Don't ask me the proof. So, let's do formally now what we observe on this example. Rather than real numbers, now the continuum will be Laurent series, formal series. So I have finitely many negative, finitely many positive powers. You notice that I put z in the denominator. That's a kind of standard. You work at infinity rather than at 0. And it's a Laurent expansion. And we call the fractional part of it when we get rid of the positive terms. We have finitely many positive terms, and we have a tail with negative powers. infinite possibly. And we can put a non-Archimedean norm here. We can do the same algorithm. What do you do with real numbers? You take the real number, extract the integral part, the fractional part you invert, you take the integral part, and we do the same thing, exactly the same thing. Now the integral part will be the positive part of the series. We continue like this. We obtain, of course, rational functions, because all this will be polynomials. Yeah, so f0, f1, f2 will be polynomials. And we remark immediately that the norm of the approximation is controlled by the degrees of the two consecutive denominators. So this was known for a long time, in the time of Euler, and was formalized starting with Gauss. And there is this very beautiful and simple observation. How do you detect that a rational function, so a fraction of two polynomials, is the approximant of the respective degree of the formal series? If and only if it matches the maximal number of coefficients. So P, let's suppose we work with a function which is vanishing at infinity or constant at infinity. P and Q have the same degree. You think like this. How many parameters do you have into P over Q? Well, exactly degree plus 1, degree plus 1 minus 1, you have exactly this 2 degree plus 1. And if the fraction, when you expand at infinity, matches the maximal number of coefficients, is the approximant. That is unique. Assuming that you have a non-degeneracy, that f is not rational. So that was known a long time ago, and entered into the numerical world as a Padé approximation, namely very classical. You have a series in 1 over z, let's say vanishing at infinity. When do you, how do you identify the continued fraction approximant of order n? If and only if the degree of this difference is less than 2n minus 1. And what Padé remarked, that's late 19th century, is that this is a linear algebra problem. You write everything in terms of matrices, Hankel matrices and so on, and is totally solvable in terms of matrices. Then in the 20th century, this had a glory. This began to be exploited by signal processing, by approximation people, and so on. And here it is. Essential in these computations, so when you take the integral part and you want to do the approximation of the rest, is the so-called Hankel matrix. You have equal anti-diagonals. And let's call it, in quotation mark, the orthogonal polynomial associated to it, this function.
Sorry, what was the last column of the J?
1z, z to the n.
Last column.
The last column, so you count how many you have here.
The missing
Yeah.
entries are 0.
It's exactly, is the same. I didn't,
The missing entries are 0.
The last
no, Cn plus 1 should be.
Oh, I see. So it goes.
I didn't write it well.
Ah.
LaTeX hiccup. Yeah, so you replace the last row by the monomials. and the main theorem of Jacobi, I'll stop soon after this and we'll have a break. We say that an integer is a normal index for the formal series if and only if the Hankel determinant is non-zero, this Hankel determinant which we had before. In that case, the convergent of degree t is precisely a multiple of this determinant. So you have a constructive way to find the denominator. And the numerator is the integral part of the denominator times the series. So here is the recipe, the algorithm. You have the coefficients, you write the Hankel matrix, you compute this, let's say, orthogonal polynomial, quotation mark, is called J. And here you are. You have, assuming non-degeneracy, you have the denominator, and the numerator is the integral part of the product. Cannot be simpler and more beautiful than that. Now, non-trivial theorem. How do we detect from a formal series that it is a rational function? If and only if these Hankel matrices are becoming degenerate from a size on, all of them. That's Kronecker. And the proof is non-trivial. So try to do it. It's a good piece of work which will explain the other part. What happens if the determinant is zero?
Quick question. I mean, this is
Yes.
unrelated.
Yes.
Even naive. Is there a counterpart of this for real numbers?
Yes, of course. A real number is
The original thing you started
a real number is rational if and only if the continued fraction finishes.
No, I know, but in terms of some Hankel matrices,
No, because we don't have a variable there.
and you could still take integer,
Yeah.
integer entry.
I don't think so. And let me finish. This is not related to us, but just to show you that what happened in the 19th century, there is this Pell equation, very well studied by number theorists, as you know. And we have, let's say, polynomial R, and we are asking whether there exists polynomial solutions to the Pell equation. Well, if and only if the formal square root of R of z at infinity admits a periodic polynomial continued fraction expansion, and only if there exists a numerator, so that this abelian integral can be expressed in terms of elementary functions. As you know, usually the abelian integrals are not elementary functions. So it's a very non-generic situation here, and was discovered by Abel. You see the year. References for this. Forgotten, but masterpiece, the 2 volumes of Oscar Perón. I don't think they are translated, the lectures on continued fraction. One volume is number theory, the other is function theory. And then a very recent, relatively recent work of Sergei Khrushchev, which presents from the Euler's point of view both numbers and functions. And just have a look, is a masterpiece in my opinion. So let's stop here and have a little break.
was good value with the frequency and the first prediction.
Yeah, if you want, I can include it.
Currently, whatever it is, it's just remember the same for
Stieltjes. He has accumulated a lot of information and examples of expansions in continued fractions. And he wrote the reference for solving the moment problem with the method of continued fraction expansion. It is a long article in 2 parts, Annales de Toulouse, and I warmly, strongly recommend it for you to have a look if you ever study moment problems. It's a masterpiece. So he considers functions of S expanded in continued fraction with non-negative entries. And the main observation is that you remember we have translations and inversions. If we do such operations, translation and inversions, assuming that all entries are non-negative, Cn has non-negative real part. The real part of this, as you compute immediately, will be positive. So this preserves the right half plane. All these operations, continued fractions. So there is something which remains in the right half plane. And his main observation, and he did it by hand, if this converges, let's say, on one point on the positive semi-axis, together with all the derivatives, or in a set of points with an accumulation point, then it converges everywhere. Now, for the students of complex variables, this is a normal family argument. Well, normal family didn't exist at that time, and he proved it before Vitali, and it's remarkable. It's probably one of the first use of compactness, as we call it today, in function theory. So already this is a convergence result which propagates from one single set, a very thin set, with an accumulation to everything.
This is a discrete Nevanlina theorem, so to say, right?
Yes.
Yeah. Okay.
Yeah. Nevanlina was way after.
Yeah. Okay.
So, in his memoir, he considers these very specific functions. And he remarks that as we saw for continued fractions of numbers, the rational even approximants and the odd approximants converge. Not necessarily to the same function, but they converge to analytic functions in the right half plane, even in the complex plane minus the cut. And in particular, you have, when you have such a convergence, the asymptotic expansion along the real line, in the sense later on of Poincaré, is precisely a formal series with what you would say the Taylor coefficients of the function at infinity. Well, this, just to jump a little, turned out to be exactly the moments of a measure. And this is a weak form of expansion. Notice that this series may be divergent, but still you have this matching when you go along the real axis to infinity of the partial sums.
Could you go back one slide?
Yes.
Could you go back one slide?
And this is called the Stieltjes summation method. So you may have, as you probably know, you may have divergent series. We'll have some examples. Can you renormalize them and make them convergent? Abel summation is one. There are many, Hausdorff summation is another. And Stieltjes proposed this one, namely expand this series into a continued fraction, and it may happen that the expansion converges rather than the series. So, when do we have indeterminateness? When the two limits don't match, the even and the odd. And this happens if and only if, if and only if the series of the coefficients there is summable. That's Stieltjes' memoir. And in particular, the limit, P and Q are now entire functions, is infinite sum of such simple fractions. If you have divergence, then the two odd and even approximants coincide, and there exists a measure which represents the respective series as a Cauchy integral. Now, if these elements are uniformly bounded, then this measure will be even supported on, we'll go into that. So it's what is called the Stieltjes transform. Interestingly enough, you know from early analysis the Riemann-Stieltjes integral. He developed the integral for this purpose. Namely, he said we need a concept of an integral which represents either a sum of point masses or a continuous distribution in a unified way. And in the memoir there is the Riemann-Stieltjes integral is developed. So we have already a criterion of indeterminateness and determinateness in terms of the entries of the continued fraction. Now the interesting part, if we look at the continued fraction,
Sorry, maybe I missed it. Where was the mu so far?
mu appears only in the very end. There is no mu yet. And notice that if you do the expansion and so on, the first n entries in this expansion depends on the first n moments. So it's a triangular transform. If you take the moments and you want to compute the entries here, it's a triangular transform. So if you have the first n moments, you can compute the rational approximant up to the order n. And you have a rational function which best approximates the series. And now a comparison with what we did is in order. Before we had the continuum, the real numbers. And now we have another kind of continuum. We have our admissible measures on the semi-line and represented by a sequence of numbers. Not the moments, but by the entries in the continued fraction. Why is this superior? As you probably know, the moments satisfy a bunch of inequalities. There are a lot of constraints, positivity assumptions, and so on. The entries here are free. And that's the big issue. The entries in the representation of a real number are free. Choose any integers here, and you will have a real number, the entries here are free. So somehow the continued fraction unwinds and detects the free parameters in representing a measure. This is the important observation.
But in half of the coefficients are constant, in the other half are linear.
Here are the entries. What I am saying here, these entries are totally free. Positive, but free. Non-negative. Now, if we jump a little, there is a constructive bijection between measures and analytic functions, probably well known to some of the people in the room here. Functions which preserve half plane, the so-called Nevanlina functions, are represented in this form by a positive measure and some coefficients. And the expansion of the series along the imaginary axis now will detect the moments of the measure sigma. Here I'm jumping a little to Nevanlin. So in particular, you can recover what I mentioned at the very beginning, and this was known to Stieltjes. You can recover the measure from the Cauchy transform. And there is this exercise with the Poisson kernel, which gives you precisely the formula. This is known now as Stieltjes-Perron theorem. Now, there are in Stieltjes' memoir, there are many interesting examples. I'll come to probabilistic ones at the end. One of them is the Stieltjes approach to the Stirling formula. So we want to approximate the best possible gamma function. As you know, you take the logarithm and you have this reminder, which is a little unfriendly. Is a Cauchy transform, or if you want a Poisson transform of this function. If you expand this in a series, this is divergent. And that's the drawback of Stirling's formula, if you know really, if you want accuracy. However, if you take the continued fraction expansion of the formal series associated to this Poisson transform, it converges. And then you can stop it at any moment, and you have really a good approximation of the gamma function up to any order you want. Now, enters Hamburger. Hamburger is really a follower of Stieltjes. He has 3 memoirs around 1920, so about 20 years after Stieltjes, where he uses continued fraction extensively and tries to understand the moment problem. And the uniqueness theorem I mentioned is derived from Hamburger from this part. I'll not expand more there. It's beautiful. They are in German, but also worth reading if you want to go deeper into details into this theory. They entered briefly into a Hieser's book on moments, but there are parts in Hamburger which are not exploited yet. So for the students, I advise you go there. So he does the convergence, what I mentioned, a la normal families. He parameterizes all solutions of the truncated problem. And he is the one who first identified the Christoffel-Darboux kernel as the key object to relate when you study indeterminateness in the moment problem. Very soon, then Van Lina enters, and he comes with a function theory approach, which will complement and complete this story. But I go to another famous function theorist, Carleman, who has a more interesting and more constructive approach, I would say, to the uniqueness problem we are interested in. Again, I am giving you today a lot of classical references. He has 2 books. The second one is of interest for us, lectures given at Collège de France. And here he complements Danjois' work on quasi-analytic functions and gives the famous criterion of uniqueness for the moment problem. So what it is about? The maximum modulus principle, well understood. Essentially Fragment-Lindelöf theorem, but even with a twist, with subharmonic functions. There is this main lemma, which gives almost everything after for free. So you have a sequence of real integer monotonic to infinity and another sequence of increasing integers, and you assume that this series diverges. An analytic function in the upper half plane satisfying a growth condition of this form. So you notice that for every n we have a link between beta and lambda. If you know a little Fragment-Lindelöf theorem, it's not surprising, is identically 0. So you have a uniqueness here. So what it is about, Fragment-Lindelöf, if you have the maximum of the function on the whole boundary, on a bounded domain, you know that the function in modulus is less than. Suppose that the maximum is missing 1 point. So you have the maximum everywhere, but at 1 point it jumps. And then you replace that with a growth condition, and that will give you the maximum principle. That's essentially Fragment-Lindelöf, what he's using here. Let's apply it to the uniqueness problem for the moment problem. So we have an admissible measure, and suppose that admits 2 solutions. We take the Cauchy transform.
Go back.
Yes, please.
So the function is defined on the right half plane, right?
No, in the upper half plane.
Okay. Any idea how this last condition will look in case the function is defined on the disk? So if we bring it by a Kelly transform or something to the disk?
At the point 1. So you distinguish the point 1, and you have 1 over z minus 1, something like this, and you map infinity to 1, and then, of course, you can put it on the disk. Of course.
So the growth condition, is it a power of 1 over z?
Is it a power of 1 over z? Yes. 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 But beta is also big. So there is a link between the density.
That's what was confusing me. You don't require the betas to go to plus infinity, right?
No. It's lambda which goes to infinity.
So that's still good enough.
Mm-hmm. So let's suppose that we have 2 solutions. We take, as we did at the beginning of the lecture, we take the difference between the Cauchy transforms. And we estimate the tail of the expansion. Why this appears? Because exactly as we did before, you multiply by z to the n and subtract an x, you have a polynomial day match there, and then you'll have only the tail of the expansion. And the tail is exactly this one. Therefore, if we look at the estimate here, we have the nth to nth moment, z to the 2 to the n, you see it, yeah, because a z comes out. You assume that you are slightly inner in the upper half plane, and you get this inequality. Now, if we take the integers as the lambdas, and Cn's will be the betas, the main lemma implies that if this series diverges, the two functions coincide. Now, what is the big advantage here? And this is his main contribution. This is a condition only in terms of the moments. The Christoffel-Darboux kernel, the Christoffel function, depends on the moments, but when you take this limit at infinity, the sum of orthogonal polynomials, you cannot grasp it. While this is very accessible. In many examples, you know the moments, and immediately you can estimate whether this is. It's not necessary and sufficient. It's only a sufficient condition, but still it's very, very valuable. And so far I postponed the construction of examples. So we speak about indeterminate measures, which are, how do we see, I didn't give a single example yet. Here is what Carleman proposes. Take a C-infinity function which vanishes at the endpoints, and the observation is that the square average of the p derivative is a Stieltjes moment sequence. Why it is so? Integration by parts. You remark immediately that this is a positive definite kernel. When you add 1 is also positive definite, very simple observation. Therefore, it is well known that these two conditions show that we are in a Stieltjes situation of a moment sequence. So we take, again, the square mean of the p derivative. And now you have the function on the interval 0, 1. Either you extended to be even or odd on the -1, 1 interval. You have two extensions. According to these two extensions, you have two Fourier series, the cosine and the sine series. For them, you have, of course, the Parseval identity, and the two series restricted on the positive interval will look like this. You agree with me? This is the cosine series, this is the sine series. But wait a minute, the 2 norm can be computed in terms of the coefficients. So M0 can be computed either from the first series or the second, and the other coefficients, the other moments, appear as Fourier coefficients in the expansion. Therefore, you have these two representations. MP are the moments. These are point masses. This charges something at 0. This doesn't. So you have two discrete measures supported on pi n, this lattice. and they give the same moments. So remember this, you can construct them very easily. And now if you want, here are the two distinct solutions. If you want absolute continuous measures for the same function, take the Fourier transform rather than the discrete Fourier transform. Take the Fourier transform, and exactly for the same reason, you will have them represented by densities. And in the end, you will have 4 distinct measures, 2 discrete, 2 absolutely continuous with the same moments. But it's much more. Dangeau proved this beautiful theorem, maybe you know, quasi-analytic. These are functions which are determined by their derivatives. Carleman used this tool, exactly what we mentioned, to prove Dangeau theorem. And here is, yes, please.
So, did Carleman extend the class, or he essentially just proved determinateness for exactly this class?
No, he completed. He showed what is the necessary and sufficient condition. Dangeau proved only one implication, and Carleman proved the other one. But then you need a rearrangement of the coefficients.
Right. But what I wanted to know is this class precisely the class for which Carleman's theory
Yes,
is?
yeah.
Exactly.
Exactly. And here is, in one slide, I'll show you for the connoisseurs here, the proof of Dangeau theorem. It's remarkable. So we take our function, we rescale it a little, and we estimate the nth derivative. The moments are exactly as you remember are the average of the square. You have this inequality. And the Carleman condition is exactly this one, which coincides with Dangeau condition. That means that the associated moment problem admits a unique solution. But this happens obviously only if phi is 0. And we are done. So it's masterpiece. Let's go back to our business. What is at stake here? And this was realized already by the founder, Stieltjes and Hamburger, is the spectral theorem. So Carleman then discusses what Hilbert and the whole school are trying to do. Namely, they look at this quadratic form in infinitely many variables, and they want to diagonalize it. This is represented in modern terms in L2 by this matrix, the eigenvalue problem. Lambda is the spectral parameter. Well, this, if you look at the zeros of this, you will immediately remark that this is nothing else than the 3-term relation for the entries. Suppose that here you have x1, x2, x3, and so on. You have a 3-term relation for, so you want the eigen functions here, the eigenvectors. They will satisfy a 3-term relation, which invites to do a continued fraction expansion. You do it. Here it is. The 3-term relation is encoded exactly in this expansion. And for instance, if the entries are uniformly bounded, a la Stieltjes, we know that the limit exists and is represented as a Cauchy transform of a measure. Well, what is this measure is exactly the spectral measure of the function. So what Stieltjes did essentially was to construct the spectral measure of a three-diagonal matrix, symmetric matrix, what is called the Jacobi matrix. And now we reach, of course, we know the spectral theorem, we know expansion and so on, but this was the beginning of the whole of theory. And this can extend to unbounded entries, and then you enter into the indeterminateness, which is exactly, I'll mention it in my fourth lecture, it's exactly the extension of symmetric operators to self-adjoint ones.
Can you go back to the matrix for a minute?
Please. So the main focus, if you look at Hilbert's work, is the quadratic form. And this is motivated by vibrating strings and so on. So it's very mechanical. And he wanted to find the principal vibrations and so on, the oscillations, and to expand into a series. And this was the beginning of the whole story.
So in place of zeros, if one put appropriate things, then it will be Hankel.
No. Especially
Lots of lambda, sure.
The matrix.
the matrix is not Hankel, obviously.
It is not.
No, it's not Hankel.
Yeah, but if one replaced zeros by appropriate things, then it would become Hankel, right?
Yeah, but we don't.
Yeah, okay.
We don't. The main object here was the quadratic form. If you look, F. Riesz has a whole book of quadratic forms in infinite variables, and it's exactly what he completed what Hilbert started.
I was just wondering if there is a characterization of self-adjoint Hankel matrices.
Well, the Hankel matrices are behind this because they represent the moments. So we deal here with symmetric Jacobi matrices. And the Hankel matrices are when you analyze the moments and so on, as you saw, Jacobi also did the Hankel matrix. But they are different parameters, very different parameters. So we have the spectral theorem essentially, and that was the beginning of spectral theory. And by the way, the orthogonal polynomials satisfy this three-term relation, as you probably know, very elementary to prove. And now this explains why we are completing the circle. The Jacobi matrix and the orthogonal polynomials come hand in hand. And what Hamburger proved, and this was what we did at the beginning of this lecture, is that if we have the Christoffel function equal to 0, then the moment problem has a unique solution. I will take more time. You announce until 12:15, right?
Yeah.
So sorry, I'll keep you a little longer, because there is more in the story. We saw already Marcel Riesz at work. It was a brilliant idea. He has 3 papers. Here is the reference you mentioned, La Troisième Note in 1923. And I put here on the slides what we already did, namely that we regard the integral as linear functional, and essentially we know it only on polynomials. We want to extend. And the extension is given by this Han-Banach type argument, induction, Zorn lemma, but was done before. That's the interesting part. And we don't need a topology here, we need only an order. So there is no semi-norm, there is only a vector space with an order, and then you can extend.
By an order, you mean you identify some cones?
Exactly, you have a positive cone with a specific property that doesn't necessarily generate the whole space, but any element in the space can be majorized and minorized by an element of the cone or the negative. Here is the barrier, what we discussed, the upper and the lower integral. And if this is equal for all continuous functions, then we are done, we have uniqueness. But he proved something much more interesting and much deeper. Namely, he analyzed from Hamburger the growth of the inverse of the Christoffel function. So suppose we are in the indeterminate case. Then this function will have, in the upper half plane, will have a positive limit. From Hamburger, he showed that everywhere this has a sub-exponential type in comparison with entire functions. So for every epsilon, there exists a constant which depends on epsilon, so that this grows no faster than epsilon to e to the epsilon modulus of z. Sub-exponential type. And he exploited this in a masterly way, genius. Suppose that we have equality for a non-polynomial. So suppose that one continuous function is not a barrier. Then there are, of course, sequences of polynomials from below, from above, which will converge in the mean, that means according to our functional, to 0. And by the definition of the Christoffel function, the evaluation at the point lambda, we fix a point, is bounded by the Christoffel function and the integral of the polynomial. But wait a minute, for this we have a growth. In the end, here we'll have an entire function if we pass to the limit. This is a sequence of polynomials. Is an entire function which has a polynomial here and the sub-exponential growth in the upper half plane. Fragment-Lindelöf, again, this maximum principle with one point missing, shows that this is 0. Cannot be. Conclusion, any continuous function which is not a polynomial is a barrier. Any. Not only there exists one. Therefore, now you have an array of choose as you like barrier, and he plays a little with this one. Why? Because for the cosine, you know very well, simple exercise, if you truncate the series, is either below or above. Easy to prove. So you have the polynomials, which are at least two sequences of polynomials below cosine, above cosine. And you have the estimate. The parameter A is arbitrary. And assume that you are in the indeterminate case. Then this has to be bounded by a constant. Pass to the lim-inf. And here you have a condition purely in terms of the moments. It's slightly weaker than Carleman, but not very much. So if this lim inf is less than infinity, the problem is determinate. Quite remarkable again. Now, a side remark for the connoisseurs here. We are in the indeterminate case. And we take the closure of polynomials in L2 of the measure. These are entire functions. We just show that this is a space of entire function. Well, this is what Debranche did. This is the origin of the Debranche-Rovniak space. The whole Debranche space started, and Crane and before and so on, with the analysis of the indeterminate moment problem and the closure of complex polynomials in L2. So it's a space of entire functions with the respective contractive flip and so on. Sorry, we go back. Just a simple example. Obviously, a student in complex analysis will identify this series doesn't converge. Clear. But if we take the continued fraction at infinity, it's easy to compute the recurrence. It's precisely this one. This is convergent. And if you want, on this simple example, this is exactly what Stieltjes proposed. You renormalize the series by a continued fraction, and you give a sense to its sum. And the limit, the measure which represents, is precisely this one. Now, higher dimensions. I will disappoint you. I'll show you some results. Nothing matches the beauty and the depth of the one variable case. And I'll give you an anecdote. Bochner, you know the name, harmonic analyst, received an award from UCLA. UCLA has a corridor with portraits of mathematicians, and the occasion of putting his portrait on the wall there are many, maybe you remember, they had a party for him, a celebration. And somebody at the party raised a glass and said, Professor Bochner, I want to drink for multivariate Fourier series. And he put down the glass and he said, I don't drink for multivariate Fourier series. We are keeping the proportion. We are in this situation. The multivariate case is incomplete, and there are only partial results. What I'm doing recently now with David Kimsey is that we extend the Hamburger criterion to affine curves. I'll not go into much detail, but if you have a polynomial parametrization, again, the Christoffel function will detect indeterminateness. And there are, so the proof is quite involved, uses, of course, Marcel Riesz barrier idea. We cannot expect this to work for rational functions. I'll not go into much details here. I will want to finish in good time. Again, the main character is the Christoffel function now along the complex curve. So you have a real affine curve. You complexify it. You take the zero set of these polynomials, but now in complex space, affine space, many dimensions. You have this curve, and for these curves, we could prove that if they have a polynomial parametrization, you have the criterion a la Hamburger. The Christoffel function detects indeterminateness. There are special curves here where I don't go into these details. So there is some geometry at the point at infinity in two variables. And for them, we show one implication, that if the measure admits analytic bounded point evaluation. That means Christoffel function is locally bounded from below, not at a point, but in a whole neighborhood. Then the measure is indeterminate. So there are, and these are beyond polynomial parametrization. Too technical. Just for your fun, I take a break here and show you how you produce polynomially parameterized curves. If you have a rational curve, it can be transformed into a straight line by such a change of variables. So you keep one variable in 2D. Or the cusp is always polynomially parameterized, as you remark immediately. T to the L and T to the K will give you the parametrization. But the interesting part that any simply connected irreducible polynomial curve is equivalent to this one. And so on. I'm looking at the watch and I want to finish. Here are some simple examples I took from our paper just for fun, to cheer you a little with some geometry. So this is low degree polynomially parameterized curves. Campiled looks like this. Rhaphoid, degree 4, looks like this. So this is polynomially parameterized, and it's not trivial, the parametrization, as you see. The quintic, L'Hôpital, looks like this. And for all this, when we take the complexification, we have the criterion with the Christoffel function, the indeterminateness. Now, to prepare my next talk, in several variables, what are the barrier functions? Well, again, here we have to rely on something we know. What transforms do not destroy the information in the measure? And one of the simplest is this Van-Tapie transform, which is analog of Cauchy, but it's not the Cauchy kernel in several variables. And it's well known that if you are supported in a convex cone, this is well-defined analytic in the dual cone. And for this one, we can play the game. So it's a uniqueness set, a la Stieltjes. And this is the barrier statement, which we know already from 1D. It remains, unfortunately, theoretical, but still there is something to put your hands on. I'll give you references. Here is an archive paper, a recent book by Konrad Schmüdgen was published by Springer, and we have a joint paper 2008, already a long time ago, about multivariate determinants. There are sufficient criteria, but nothing necessary and sufficient so far. And to finish, in 5 minutes, probability theory. Yeah, Christian Berg. You will be surprised that very common probability distributions are indeterminate. You know the Gaussian very well. Take a random variable which has this density and take powers of it. All odd powers, starting from 3, are indeterminate. And if you take the modulus of it, that means you put the distribution on the semi-axis, is precisely indeterminate for a power bigger than 4 and determinate for the exponent less or equal than 4. It's a very short paper. I'll show you the reference of Christian Berg. And what is interesting here that you have indeterminateness both in Stieltjes and Hamburger sense, what does it mean? That you restrict the supports on 0 infinity or on the whole line. You may ask, you start with a measure on 0 infinity. Are there equivalent measure with the support there? It may happen that you have others, but only on a bigger support. Well, this is on both. And this is really used by applied probability people, the log normal distribution, this function. And believe it or not, this appears in the memoir of Stieltjes. So he proved with the residue theorem that this density, try your hand. If you have students in complex analysis, try your hand to prove that for any R, the moments of this density are the same. That means this is orthogonal to all monomials, all polynomials. References for this part, very beautiful Christian Berg short note. Jordan Stoyanov wrote quite a lot on different methods to construct indeterminate measures from the probability point of view. And he has a book on counterexamples in probability, which is quite interesting. And the first note is about the difference between Stieltjes and Hamburger determinateness. So I'm looking at the watch, and let's stop here. Thank you.
More questions?
So I see that paper is very short. Can I ask you, how does that proof goes work?
It's direct orthogonality. So it's a computation of the moments to prove that it's unique for the respective powers. You use Carleman. He uses Carleman criterion. The other one, he uses orthogonality of again a sine or cosine function. It's 3 pages. It's very readable.
There are no further questions, please. The next talk is on Friday.